An invisible atmospheric zipper can suddenly rip open the sky, unleashing tornadoes with shocking speed and ferocity. This powerful, concentrated convergence transforms seemingly calm conditions into catastrophic severe weather events in mere moments. Understanding this hidden meteorological mechanism reveals how destructive storms materialize from ordinary air masses above us. Earth's atmosphere is a dynamic, swirling ocean of air, constantly mixing different temperatures and moisture levels. These distinct air masses often meet along invisible boundaries, like seams in a giant, chaotic blanket covering the planet. Such atmospheric fronts, though unseen, represent immense potential energy, waiting for the right trigger to become active and powerful. For centuries, people have observed sudden, inexplicable weather changes, often wondering about their rapid and intense formation. Scientists discovered that these boundaries are not always gentle interfaces. Sometimes, they act like a powerful atmospheric zipper. This zipper effect describes a specific, potent interaction between air masses that rapidly intensifies storm development. When these atmospheric seams collide or merge, they create a focused channel of upward motion, lifting vast quantities of air.
Viewers should care because this phenomenon often dictates where and when the most dangerous weather, like supercells, will form.
It explains why some areas experience calm conditions, while nearby regions are suddenly ravaged by intense, swirling tempests. Grasping this concept provides crucial insight into the rapid escalation of severe thunderstorms and their devastating consequences. It highlights the intricate dance of forces within our atmosphere, leading to some of nature's most spectacular and terrifying displays. The zipper effect begins with the formation of distinct atmospheric boundaries, such as a cold front or a dry line. A cold front represents the leading edge of a cooler, denser air mass pushing into warmer, lighter air, forcing it upwards. Conversely, a dry line marks a sharp contrast between moist air from the Gulf of Mexico and dry, desert air from the west. Imagine these boundaries as two massive, invisible walls of air, each carrying different properties of temperature and humidity. These distinct atmospheric features move across the landscape, sometimes converging and interacting with surprising, violent energy. But the real danger emerges when these boundaries perfectly align, setting the stage for an even more dramatic transformation. The key to the zipper effect lies in the way these boundaries are pulled together, much like the teeth of a physical zipper. When a dry line encounters an outflow boundary from an earlier thunderstorm, their combined forces create a new, potent convergence zone. An outflow boundary is essentially a miniature cold front, formed by the cool air spreading out from a dying thunderstorm. As these two boundaries approach each other, they don't simply merge. They actively reinforce the lifting mechanism between them. This convergence creates an accelerated upward motion, a concentrated corridor where moist, unstable air is rapidly forced skyward. But that's not the strangest part. This intensified lifting acts like a powerful vacuum, drawing in even more moisture and energy. Think of it like a giant atmospheric vacuum cleaner, sucking up all available ingredients for powerful storm development. The rapid ascent of this warm, humid air cools it quickly, causing water vapor to condense and release latent heat. This released heat further fuels the updraft, creating a positive feedback loop that intensifies the vertical motion even more. A crucial ingredient called wind shear then plays its part, describing how wind speed or direction changes with altitude. This shear helps to organize the rising air, causing it to rotate and preventing the storm's updraft from being choked by its own precipitation. Tornadoes and large weight hail until you hear what comes next. This organized rotation is the very foundation for the development of supercell thunderstorms. Supercells are long-lived, tornadoes and large weight hail. The zipper effect essentially provides the perfect conditions for these formidable storm engines to ignite and sustain themselves. It creates a narrow, elongated zone of concentrated lift and instability, acting as a linear incubator for severe weather. The stronger the initial boundaries and the more unstable the air, the more explosively this atmospheric zipper can operate. This precise alignment of atmospheric forces transforms a seemingly innocuous boundary interaction into a catastrophic weather event. And then something unexpected happens. The storm itself can generate new outflow boundaries, potentially creating new zipper points. This allows a squall line or supercell to propagate and regenerate, maintaining its intensity for extended periods across vast distances. Meteorologists meticulously track these interacting boundaries, recognizing their critical role in forecasting severe thunderstorm outbreaks. Without this zipper mechanism, many of the most devastating storms would simply fail to achieve their full, destructive potential. It underscores the incredible complexity and hidden power within the seemingly ordinary movements of Earth's atmosphere. The immediate impact of the zipper effect is the rapid formation of severe thunderstorms, often escalating into supercells. These storms unleash a devastating array of weather phenomena, including large, destructive hail and powerful straight-line winds. Most critically, the atmospheric zipper frequently becomes the birthplace of violent tornadoes, capable of leveling entire communities. Imagine homes, businesses, and infrastructure being torn apart by winds exceeding 200 miles per hour, all because of this effect. Agriculture also suffers immensely, with crops flattened and fields destroyed, impacting food supply and local economies significantly. The sheer speed of development means people often have very little warning, making timely evacuation and preparedness extremely challenging. This mechanism directly contributes to human safety concerns, demanding constant vigilance from weather forecasters and emergency services. Understanding the zipper effect allows meteorologists to better predict where these dangerous storms are most likely to erupt. Improved forecasts provide precious extra minutes for people to seek shelter, ultimately saving countless lives during severe outbreaks. It highlights the profound importance of atmospheric science in mitigating the risks posed by our planet's most extreme weather events. The intellectual payoff comes from deciphering such intricate atmospheric puzzles, revealing the hidden order within climatic chaos. This knowledge empowers communities to build more resilient infrastructure and develop effective response plans for storm emergencies. Ultimately, the zipper effect serves as a stark reminder of nature's immense power and our continuous need to comprehend its intricate workings. It's a testament to how subtle atmospheric interactions can cascade into events of monumental, life-altering significance across the globe. The atmospheric zipper effect fundamentally explains how converging air mass boundaries can rapidly ignite and intensify severe weather. This critical mechanism underscores the complex, yet predictable, processes behind some of Earth's most destructive and awe-inspiring storms. Continued scientific inquiry into these phenomena helps protect lives and property, enhancing our resilience against nature's fury. If you found this intricate atmospheric dance fascinating, subscribe for more incredible stories about our dynamic planet. Let me know in the comments what weather phenomenon you find most surprising, and hit the like button if you learned something new.